The whole of mathematics is just a product of simple logic. If this, then that. Building up from almost nothing. That merely clever application of simple logic can yield so much is a testament to the power of logic. The concept of probability, like any other part of mathematics, is also built on pure logic. But one needs to look at various possible options very carefully and make sure the logic is being applied correctly. In particular, one needs to figure out what all are the possible ways for something to happen. For example, a coin toss can result in either head or tail. Which all of them are equally likely to occur? For a fair coin, both are equally likely. And whether occurrence of an event affects the likelihood of another event. For example, if a coin is tossed and a dice is rolled, outcome of coin toss does not affect the likelihood of getting a 6 on the dice. What fascinates me is the question of probability never ceases to challenge me. It is so easy to get into a wrong logic which appears so silly once the error is identified. I will discuss a sample question to arrive at a logical answer. Logical in quotes, because while it may appear to be perfect logic, later once we discover the mistake, it might sound so silly. See if you can spot the error of logic. I will then explain the error and then correct the error to arrive at the corrected answer. I hope you find it fun to follow. Question. There are 10 persons in a room, none of them born on 29th February. Let's exclude 29th February because that complicates. Each person's date of birth, date and month, excluding the year, is random, which means it is equally likely to be on any of the 365 days of the year. What is the probability of finding at least 2 persons having the same date of birth? My logical answer goes as follows. Let's call those 10 persons P1, P2, P3 up to P10. When the question is about at least 2 persons, a common technique is to find the probability of no 2 persons having same date of birth and then subtract it from 1. Take the first person, let's call him P1. He will have some date of birth. Pair him with each of the remaining 9 persons. The probability of each pair not having same date of birth is 364 by 365. There are 365 days in a year. P1 has already occupied 1 day. So for P2, randomly chosen, not to fall on the same date as on P1, he has 364 options left out of a possible 365 options. So the probability is 364 by 365 for each of them. Since the result of the first pair does not affect the probability of the second pair, the probability of any of the 9 pairs not having same date of birth, that means all these events should occur. This event of not having the same date of birth, this event of not having the same date of birth, all these events should occur. There are 9 events. Each of them does not depend on any other. So for 9 events to occur simultaneously, the probability is multiplication of all these probabilities, which works out to 364 by 365 to the power 9. Now we are done with person P1, exclude P1. Take P2 and pair him with each of the remaining 8 persons. We are excluding P2 pairing with P1 because that has already been done. Again, P2 will have some date of birth. The probability of this pair not having a common date of birth is again like before 364 by 365, which same holds true for all the 8 pairs now. And by the similar logic, all these 8 pairs, none of them having the same date of birth, is 364 by 365 to the power 8. This time 8 because there are 8 pairs. Continue the exercise, take the third person, which will be P3, pair him with all possible remaining options. Probability will work out to till you have ninth person. You have only one person to pair him with, and the probability is 364 by 365. To arrive at the probability of any of the above pairs, P1 paired with remaining 9, so 9 pairs, P2 paired with remaining 8, so 8 pairs. So none of these, since I'm trying to find out no two persons with the same date of birth. So all these events should happen. This should happen, and this should happen, and this should happen, and this should happen. So I will multiply all these probabilities. This works out to and this 9 plus 8 plus 7 up till 1 is equal to 45. So the probability is 364 by 365 to the power of 45. Hence, at least two persons, at least one of the pairs having a common date of birth is 1 minus this. So the probability is 1 minus bracket 364 by 365 to the power 45. Seems logical? By the way, this is not the correct answer. How do I know? Logic again. Supposing if we had 366 persons in the room, going by the above method, the probability of at least two persons having the same date of birth will work out to 1 minus 364 by 365 to the power 365 plus 364 plus 1, which is a pretty this 364 by 365 to the power 365 plus 364 plus 363 plus 1. This is a very large number, hence 364 by 365 raised to that power will be very small number, and 1 minus that very small number will be very close to 1, but as you can see it is not 1. 364 by 365 raised to any power, no matter how large, will never become 0, and 1 minus this will never become 1. So the probability with 366 persons in the room, this logic says still the probability of having at least two persons same date of birth is still not 1. But is this not wrong? If there are 366 people, do you have any choice? You can allocate 365 different dates to 365 people, but the last person, 366th person, will have absolutely no choice but to have a common date of birth with someone else. So the probability should become 1. By this result, it does not become 1. There has to be some mistake. Where is it? Even if you know of a different method to solve this problem, you can say, okay, I don't care about this method, I have another method, this, that, and all. The challenge here is to identify the error in this logic. See if you can do that. Let us revisit the logic again. Take the first person, let's call him P1. He will have same etc logic. This first step, I see no problem with this logic. So first person not sharing date of birth with any of the remaining persons, probability is 364 by 365 to the power 9. Now we come to the second person. Did this event impact the probability here? Do we know anything by now which will change our assessment of the probability? We know that P2, P3, P4, P10, none of them had this date of birth. So this guy P2 has, his date of birth is any one of the remaining 364 days, not one of the 365 days. The guy, this P2 has, his date of birth is one of the remaining 364 days, not one of the, not all 365 days. Same applies to P3, P4, P5 and P10 also. None of them. P2 to P10, all these persons. When we come to step 2 and we say, in the first step we did not find any pair which had a common date of birth. This obviously meant while P2, P3 up till P10 may or may not have a common date of birth, none of them has a common date of birth with P1. That means P2 till P10, their date of births options are limited to 364 possibilities. So P2 gets one of those 364 days as his date of birth, and then the probability that P3 does not overlap with his date of birth is now 363. He has remaining 363 days to choose from so that he does not overlap with P2. One day is already taken by P1. One more day has been taken by P2. P3, if he has a compulsion of not matching his date of birth with P2, and we already know it did not match with P1, he has 363 days to choose from. So this probability, instead of 364 by 365, this is 363 by 364. Same applies to all these 8 pairs. And here, the probability of these 8 pairs, none of these 8 pairs having a common date of birth, is 363 by 364 and not 364 by 365 as we argued before. And let's say in these 8 pairs also, none of them had a matching date of birth. So what do we know when we reach step 3? We know P1 had some date of birth and none of these guys, remaining 9 guys, had that date of birth. P2 had a different date of birth. That we know already here. P2 did not have the same date of birth as P1. P2 had a different date of birth. And then again, none of these remaining 8 guys had this date of birth. So these 8 people now have got remaining 363 days to choose from. So when you come to P3, his date of birth is 1 out of 363. And when we pair him with any of them, each of them has got only 362 remaining options such that he doesn't overlap with P3. So here the probability becomes, when we came to step 3, we knew P1 and P2 have got 2 different dates of birth. So all these guys from P3 to P10, their dates of births exclude these 2 days. So they have got 363 possible options, each of them. P3 takes one of them, and then for the remaining 7 persons not to match with P3, they have got only 362 options. So 362 options out of the 363 options available for each of these pairs is a situation where the date of birth does not match. And if you continue this logic, 364 by 365, 363 by 364, 362 by 363, what we get here, with P1 it was 365 minus 1, with P2 it was 365 minus 2, with P3 it was 365 minus 3, with P9 it must be 365 minus 9, and the denominator has to be 1 more than that. 365 minus 8. Substitute these values here. What do you get? 364 by 365 to the power 9 is alright. Here it is 363 by 364 to the power 8, and goes on till we get. Now this is 364 to the power 8, and this is 364 to the power 9. So I am left with only 364, and this part gets cancelled. This numerator 365 to the power 9 remains. So this is gone, this is taken care of. Here I have got 363 to the power 8. In the next term, in the denominator, there will be 363 to the power 7. That power 7 will cancel with this 363 to the power 8, and I will have 363. And this will continue. Only single powers of each of these terms will remain. The denominators of each of these terms will cancel out with the previous term, and the last term, this 357, will cancel out with the previous term, and I will have 356, and the denominator becomes 365 to the power 9. So the probability works out to 1 minus 364 into 363 into up till you get 356 divided by 365 to the power 9. So I claim that this should be the correct probability of at least 2 persons having the same date of birth. How many terms are there here? 364, 363, and this is 365 minus 1, the first term, and the last term is 365 minus 9. Now let me do a cross check with 366 persons in the room. This one remains same. This power 9 becomes 366 minus 1, that is 365 to the power 365. Alright. And then I begin with 364, 363, and the last term I get is 365 minus, remember, 366 persons. For 10 persons it was 365 minus 9. For 10 persons it was 365 minus 9. For 366 persons it will be 365 minus 365. So the last term here becomes 0. Multiplied, all these numbers are multiplied, so this whole thing becomes 0. So the probability is 1 minus 0, which is 1. That means you are sure to have at least 2 people with same date of birth. Common sense matches with common sense. If there are 366 persons, at least in the worst case, 2 people will have to have the same date of birth. Now notice how we went on a wrong path of logic. This event did impact the probability of this event, which we had overlooked. Hope you enjoyed this.